Bueno, muchas gracias por venir. Bienvenidos a esta última conferencia del ciclo sobre física del cosmos. Y tengo el placer de presentar al profesor Konrand Kuijken de la Universidad de Leiden. Es director del Observatorio Astronómico de la Universidad. Konrad hizo su tesis doctoral en Cambridge, en el Instituto de Astronomía de Cambridge, y después pasó diferentes estancias postdoctorales en CITA, en Toronto, donde coincidimos un tiempo, y después estuvo en Harvard, en el Kapteyn Institute en Groningen, y después posteriormente consiguió una plaza de profesor en Leiden, desde donde está ahora. El profesor Konrand Kuijken es un experto en la dinámica de galaxias, dinámica gravitacional de galaxias. Empezó su trabajo estudiando la dinámica de las estrellas que orbitan alrededor de las galaxias para entender cuál es la materia que creaba esos movimientos, y luego ha pasado a trabajar en el tema que nos va a hablar hoy de lentes gravitacionales, uno de los efectos más sorprendentes predichos por la teoría de relatividad de Einstein, y que es una de las mejores sondas que tenemos ahora para entender cómo está distribuida toda la materia del universo, y en concreto tanto materia visible como la materia oscura, que es de lo que me imagino que va a hablar ahora en más detalle, el sector oscuro del universo. Así que ya sin más, le doy la palabra al profesor Kuijken para que nos ilustre con su charla. Y luego tendremos un turno de preguntas.
Can you hear me? So thank you very much for the introduction. Thank you very much to the Foundation for inviting me to come and talk about my work here. And thank you all for coming this evening. It's always nice to talk to a full hall of people. So what I would like to do today is take you along on where we are in our knowledge of the universe on the very largest scales, and in particular how we can make the next steps and make new measurements to try to understand even more some of the many mysteries that the universe keeps on throwing at us. And in particular, I'm going to talk about the effect of gravitational lensing, which is one of the latest techniques that we can now use to really try to make this next step. But before I can explain to you what gravitational lensing is, I'll start with a little bit of background. Let's see if this works. Yes. So the background information is that we live in an expanding universe. The distant galaxies are moving ever faster, ever further away from us. And this is a consequence of the fact that the universe started at a particular point in time, about 13 billion years ago, in what we call a hot Big Bang. Everything was very dense, was very hot, was very uniform, everything very close together, very different from the universe today. And out of that, this expansion started. The universe got cooler, got less dense, and as it cooled down, structures could begin to form, which in the end ended up with this room here, people like us trying to understand what on earth we see when we look around at the sky. And this number of 13 billion years ago may seem like a lot. It's kind of difficult to imagine. For reference, it's about 3 times the age of our solar system. So our sun has actually seen a large fraction of the history of the universe in real life, so to speak. And so as astronomers, as cosmologists, what we try to do is to understand why the universe looks the way it does, why we see galaxies, why we see stars, why these stars have planets, and so on. And in particular, what I'm going to concentrate on here is not so much, this is a picture of the entire sky, it's not so much this band here, which is the galactic plane, it's our own Milky Way, our own galaxy, but it's really what goes on when you look away from the galaxy in other directions, very far into the universe, and see lots of other galaxies and how they are distributed and how they evolve. That's really going to be the topic of the talk today. And modern cosmology really started not so long ago, maybe 100 years ago, something. The last century has really been incredible if you think back to see what big steps our knowledge has taken. And in particular, about 100 years ago, 2 things happened almost at the same time, and sometimes it's these coincidences in science that drive big progress. One of the things that happened was observational. People were beginning to be able to measure spectra of galaxies, and from that you can figure out how fast the galaxies are moving away from us or towards us. And some of the first people who did this were Slipher and Hubble in the United States. And they discovered that most of the galaxies are moving away from us. It's not that motions are random. There's a definite tendency for galaxies to move away from our own Milky Way. You get a picture a little bit like this. If we are this galaxy in the middle here, then all the galaxies around us, on average, are expanding away from us. That's the expansion of the universe that they saw for the first time about 100 years ago. At the same time, Einstein was working on his theory of relativity, and one of the inescapable conclusions from this, and Einstein himself needed some time to get used to this idea, one of the inescapable conclusions was that we live in a dynamic universe. The universe as a whole is a dynamical system, is an entity. It's not a static thing inside which things happen, but the universe itself has a dynamics, has an evolution. And so the fact that at the same time people discovered an expanding universe and people had a new theory of gravity which more or less predicted this meant that these two things very quickly gelled together into forming the basis of what is now our modern picture of cosmology. It's interesting to think what would have happened if these things had happened 50 years apart. It could well be that things could have gone very differently. So this expansion of the universe is something that's been studied for about 100 years, and it still goes on today. And we're able to do this better and better with new techniques and better measurements. And in essence, what we call Hubble's law is this relation between how far away a galaxy is and how fast it moves away from us. So if you imagine making a graph of distance to us and expansion velocity away from us, then you find that most galaxies lie on a diagonal line. The further away, the faster they move away from us still, right? Now, to be able to measure this in detail, accurately, to study this in more detail, you need to be able to measure good distances and good velocities, obviously. That's the only way you can make this graph and study and analyze it. And so to measure distances, we need something called standard candles. Basically, you need to be able to see something in the universe, and if you know intrinsically how much light it emits, and you can calculate how much light you receive from it, that gives you enough information to tell you how far away the source is. If you imagine a car light, you see a car driving towards you, then you will see the car lights getting brighter and brighter and brighter. The lights are equally bright, but you receive more light from them as they become closer. So it's the effect that the flux you get from a standard candle depends on distance. And in particular, in cosmology, we use very bright stars, exploding stars called supernovae, as our standard candles, because you can see them very far away and because we understand their intrinsic brightness very well. To measure velocities, we use something called the Doppler effect, and this is something that's familiar to everybody who walks down the streets of Madrid. You hear the cars zooming past you, and they drive pretty fast around here. And when they come towards you, you hear a high pitch, and when they move away from you, you hear a low pitch. It's this effect. That's the Doppler effect. I'm not going to do this again. And in particular, because all the galaxies are moving away from us, all the light is moved to longer wavelengths. The frequencies go down, and that's what we call a redshift. And this redshift is our fundamental measurement that you can take by taking a spectrum of a galaxy that tells you how fast it's moving away. And so a graph like this is really a graph of redshift on this axis versus luminosity on this axis, but we translate that into distance and expansion velocity. And the way to think about this expansion is sketched down here. It's not that everything is moving away from us. There's nothing special about us. It's that everything is moving away from everything else. The universe as a whole is expanding, and so you can imagine the universe drawn on graph paper, and you see that the graph paper itself is what's getting bigger and bigger and bigger. And no matter whether you take this red galaxy or this green galaxy or this blue galaxy, all of them will have the same effect that everything around them is expanding as time goes on. So that's the expanding universe which we are in. And nowadays, modern measurements of this Hubble diagram, this distance versus velocity diagram, are really getting very accurate. You see here, this is a modern measurement with supernovae from about 10 years ago, and you see that we get this very nice linear Hubble law that I talked about. And I will come back to this diagram later. Now, if you look at this diagram, what you see, for example, is that objects which are at a distance of 500 megaparsecs, and megaparsec is a unit of distance. 1 parsec is about 3 light years. 1 megaparsec is about 3 million light years. That objects at this distance move away from us at about 30,000 kilometers per second. And again, these are kind of astronomical numbers that it's better not to think about in too much detail because actually you cannot imagine them. You can just get used to them. But so objects 500 megaparsecs away move 30,000 kilometers per second away from us, and that means we can do a very simple calculation. We can ask, what happened? How did this galaxy, which is moving away 30,000 kilometers per second from us, it's now at a distance of 500 million parsecs. How long did this galaxy take to get there, given that we all started very close together? And just like you can calculate how long it takes to drive from here 400 kilometers away when you go 100 kilometers per hour, you can do that same calculation here, and you find that you simply have to divide the distance by the speed to get the time. So 500 million parsecs is 1.5 times 10 to the 22 kilometers. Again, one of those astronomical numbers, don't worry about it. You divide it by 30,000 kilometers per second, and you end up with almost a trillion, a European trillion seconds, which corresponds to 13,000 million years ago. And so that's why we say the age of the universe is about 13 billion years ago. It's because that's how long it takes for a galaxy moving at this speed to get as far away from us as we observe it. Basically, just running the film backwards, calculating backwards, that's when everything was at the same time. That's when this moment of a Big Bang would have had to take place. And this is an important point. The universe has a finite age. Also, light travels at a finite speed. Light travels very fast. It travels 300,000 kilometers per second, 1 light year per year. It's a very high speed, but it's not an infinite speed. And that means that in these 13 billion years that the universe is old, light has only been able to travel 13 billion light years. And that defines what we call a horizon. It's impossible to look further away because light from further away simply has not had time to get to us yet. Right? So that we can only see a finite part of the universe, which is a pity. We always want more. But there's an aspect of this which is actually very interesting because we see the things further away. We see them when their light was emitted, which is a long time ago. And so as we look to galaxies further and further and further away, we see light that's older and older and older. And so we're actually observing the universe at an earlier and earlier moment compared to the present. And so in some sense, when we do cosmology, when we look at distant objects in the sky, we are really reading a history book. We're looking at how the universe was, not how the universe is. And the further away we look, the further back we look in history. And this is a great luxury to be able to do this. And so that's why in cosmology, certainly, astronomers always want more, and we always want bigger telescopes. In many cases, that's because we want to study objects in more detail. In cosmology, the reason is actually different. The main reason to build bigger telescopes is that we can look further away. But the further away in itself is not so interesting because other parts of the universe are probably similar to ours, but it's because we can look backwards in time that way. We can observe the evolution of the universe directly by looking at light that's been traveling for many millions of light years. And so those are really the tools of cosmology. We can look back in time, and we can take pictures and look how things change as we look further back in time. And if we take this to the extreme, this is the oldest light. This is a map of the oldest light in the universe that we have. It's called the cosmic background radiation. And it was emitted when the universe was about a little bit more than 1,000 times smaller than it is now, when everything was 1,000 times closer together than it is now. A long, long time ago. This is a few 100,000 years after the Big Bang, and now we are a few thousand million years after the Big Bang. And if you look at this light, this is again the entire sky. And if we look at this light, we see a universe that looks extremely different from the way it looks now. This is a very exaggerated picture. In fact, the universe was extremely homogeneous. In all directions where you look, you basically see the same thing. The temperature everywhere was about 3,000 degrees. And the differences between the blue regions and the red regions here are about 0.03 degrees. So, here the temperature might be 3,000 degrees, and here the temperature might have been 3,000.03 degrees. So extremely uniform, very, very tiny differences between different parts of the universe. And from that very uniform, very boring, very dull universe where there was very little structure, very little anything, just a hot plasma sitting there and expanding, we got to the current interesting, very highly structured universe that we see today. So this is what we see now. Very different. This is now not exaggerated. This is really, white regions really are empty, and black regions really are full of galaxies. This is a map of a few 100,000 galaxies in the immediate surroundings of the Earth, which is, everything is relative, of course. This is a few hundred megaparsecs around us. And what we see here is that the galaxies are not uniformly distributed like this previous map was. The galaxies are very clumpy. There are regions where there are no galaxies at all, and there are regions where many galaxies are sitting together. You can see large structures. And a typical structure is these kind of empty bubbles with filaments of galaxies all around them. It's a little bit like a foam. It's like a soap. If you look at the foam in a bath, all the little soap bubbles, it's like the galaxies are sitting on the surfaces of soap bubbles. It's that kind of structure that you have to imagine. And so the question is, how did we get from here to here? That's really one of the central questions of modern cosmology. And we think we understand the answer pretty well, at least globally. And the main mechanism is what's called gravitational instability. So the effect is very simple. If you imagine that the universe is more or less homogeneous, but not quite, so there are some regions where there's more matter and some regions where there is less matter. So let's say that this is a dense part of the universe and this is an underdense, a less dense part of the universe. And then what happens is all these things attract each other through the force of gravity, and the more massive things have a bigger gravitational pull. They pull more strongly than these ones. And so what you find as time goes on is that everything is attracted towards the more massive regions. And so the effect of that is that the more massive regions get even more massive. They attract yet more mass. And so the regions in between them get emptier. And that's how you get this kind of structure, we think, of empty regions and concentrated regions in between. And since this is a series that's sponsored by a bank, I have to be very careful how I say this, but there's a human analogy to this effect, which is that the rich get richer. If there's a lot of mass in one place, it just attracts even more mass around it. And I think with money, something similar happens, but I'm not an expert. So. And here is a simulation done on a computer of one of these gravitational instability pictures. This is a picture that's made by taking literally hundreds of millions of particles, putting them in a computer and letting them evolve under the gravity of all the particles combined. And this started when the universe was about 20 times smaller than it is now. And then when you start the clock, you see that very slowly the regions where there was a little bit more mass, where it's a little bit brighter on this picture, start to suck in the material from all around them. And structures begin to form as the clock runs forward. These red regions are ones where there's essentially no matter left. And everything you see is feeding into these highly dense regions, which get more and more dense and attract more and more material. And just purely by this very simple recipe, it's just the gravitational law, no other ingredients. We end up building a structure which looks remarkably like the map of the galaxies that I showed you before. Right? You see very empty regions, filaments around them, clusters in the middle, and basically the same foamy structure that we get also when we measure the distribution of real galaxies. And it's this comparison which we can now both measure in great detail by measuring many, many galaxies and also calculate in great detail by doing huge supercomputer calculations. You can check the match of these things with advanced statistical techniques, and the match is really very good. So we really think we understand how gravitational instability is able to start from a very smooth distribution of matter into the kind of distribution on large scales that we observe. So this is actually quite a triumph of cosmology, I would say. But there's always a but. And the but in this case is that to make this work, to make this degree of clustering as extensive as what we see in real galaxies, you actually need to put in much more matter than we know of. You have to add a lot of unseen material, which adds to this instability picture with its own gravity. And in fact, you have to add about 6 to 10 times as much matter as we know is there in terms of stars and atoms and whatever, and gas. Only by adding a lot of extra material, which doesn't shine because otherwise we would have seen it, so we call it dark matter, are you able to reproduce the large-scale structure distribution. And for other arguments, which I don't have time to go into now, it turns out that this dark matter, in fact, also doesn't fit in the standard nuclear physics, in the standard particle physics that would have gone on in the early universe. So this is not simply adding more matter, but it's actually adding a very different fundamental component to the content of the universe to make this gravitational instability picture work in detail. And so this is, in fact, not a new idea. Already for 30 years now, since the 1970s, 1980s, we have known that when you look at a picture of a galaxy like this, where you see all the light that you see is from individual stars, hundreds of thousands of millions of stars, all shining, forming a whole galaxy. We now know that if you try to understand in detail how the structure of this galaxy is, then you have to consider that it sits in the middle of a very extensive bath of dark material, of extra mass, which doesn't shine, but whose gravity we can clearly feel when we analyze the motions of such a galaxy. So also on the scale of galaxies, but also on the larger scales, we need to live with this concept of dark matter, extra material that's there in the universe that doesn't shine, but that certainly takes part in generating the gravitational fields that we observe in the universe. So much for dark matter. The second important ingredient in our current picture of cosmology comes from measuring this Hubble diagram, the distance versus expansion velocity plot that I showed you before. The fact that there was a lot of dark matter predicted means that you can try to measure this in other ways, and one way to try to measure this is to think of the fact that if the universe contains a lot of matter and it's expanding, all this matter is trying to attract each other through its gravity, and so that should slow down the expansion. The gravity will try to break the expansion effect. And this is actually something you can calculate exactly in Einstein's theory of relativity. It's a prediction of the whole picture. And so you can try to measure this. You can try to see, can we measure this expansion? Can we try to measure, by looking back in time, how this expansion is slowing down? And can we, from that, deduce how much dark matter there is? And is it consistent with what we infer we need to build a large-scale structure in that movie I showed you before? So there were a number of experiments. In fact, people have been trying to do this for 50 years at least. A number of experiments to try to measure the expansion history of the universe by looking further and further back in time and looking at these precession speeds. And in fact, it was quite interesting. It could have very profound consequences because in theory, it's possible that there is so much dark matter, so much matter in total, that the whole expansion of the universe could one day stop completely, after which everything starts to contract again. And then not only would we come from a big bang, but we would end up with what's called a big crunch. Everything would get back together again, back high densities, and everything we have so carefully built would be destroyed again. So there were good reasons for trying to measure this thing. And basically the idea is the more slowing down you measure, the more gravitational pull you infer, and hence the more matter you infer is there to cause this gravitational pull. And so many of these experiments were done. Many of them didn't work. It's actually very difficult measurements. But now, since a while, we know that these measurements can be made, but that the result is completely unexpected. Instead of measuring a deceleration to a lesser or greater degree, what the outcome actually was an acceleration. The expansion is not being slowed down at all, but there is something that makes the expansion increase, accelerate, go faster and faster and faster. Something that gravity, as we understand it, cannot do. And so this is the concept that we call dark energy. And again, we are very good at giving names to things we don't understand, and that's really what we've done in this case. It's not something to be proud of, but at least it's something. So this is the illustration of those observations. This is the Hubble diagram I showed you before for nearby supernovae out to 500 megaparsecs. That corresponds to this part of the diagram here. When people measured more distant supernovae, they got a characteristic curve which you can compare to what you would expect in the bottom two cases, which is basically the range that you expect in case of, there's a lot of deceleration or not so much deceleration, depending on how much matter there is in the universe. And what they found was that neither of these curves fitted, that instead you had to go here to explain the data. And those are curves where there is a lot of acceleration, where the expansion somehow is being pushed more and more and more. And this is, in fact, what the Nobel Prize for Physics went to this year, for this particular experiment on supernovae to try to make these measurements. This really is the measurement that firmly put this idea out there. It was, nobody disputes the measurements anymore. It's really clear that this acceleration effect is there, and we have to live with it. We have to try to understand it. And so this is our picture of cosmology in one diagram, and it's really a big mystery, actually. But if you try to explain both how the background radiation, which is so very smooth, could turn into the structure that we observe in the galaxy distribution today, and the Hubble diagram for the supernovae that I just showed you, then you end up with this kind of a picture that the universe consists of about 25%, 26%, 27% of matter, of which most is in a form that's dark, that we don't understand, whose physics we don't understand, and that about 3/4 is in this form of dark energy, which is what gives you the acceleration of the expansion. And this diagram is sometimes called the pizza that nobody ordered. Right? If we had had the choice in designing a universe ourselves, I don't think we would have picked this. But I guess we didn't have a choice. And so, as I said, it's not something that we have to be proud of particularly. I think the measurements are very good. Our picture is very clear. But, we understand this little blue wedge. We understand the physics of 4.6% of the content of the universe. And in particular, the news out of CERN this week that the Higgs particle may have been found all fits in the same small section of the universe whose physics we understand, the standard particle physics model. All the rest, this 23% of dark matter and the 72% of dark energy, are things that we actually don't have much of an idea of what the physics is. And so for this situation, there is actually a technical term. And I understand many of you are listening through simultaneous translation, so I would like to give this man a small break by giving you the technical term in Spanish, and the technical term is this one. Right. We really are not, we've made fantastic measurements, but we haven't actually made great progress in understanding what they mean. So how can we make progress? Well, we can wait to see whether there are new physics ideas that somehow provide clues for how to explain these things. But in the meantime, we would also like to make better measurements to try to figure out more of the properties of this dark matter and more of the properties of this mysterious dark energy component. And so in particular, we can try to make much better measurements to try to figure out exactly how this expansion history worked. That's Hubble diagram of the supernovae. There was still some uncertainty there. We can certainly try to do better there and learn whether this acceleration has always been there, whether it started recently, whether it started abruptly, whether it's slowing down, all these things. Basically characterize it in more detail. We would like to measure how the dark matter is distributed in more detail so we can compare it to the simulations that we can do. And we can try to measure how the large-scale structure formed. We can try to look back in time and see how fast this large-scale structure grew, and again try to compare that to our theoretical models and see if the influence of dark energy on that process can be detected somehow. And so for that, we have to use the standard tricks that I described before. We look further and further away, which means looking further and further back in time, and we try to make measurements that tell us something about the expansion of the universe and of the matter distribution. And that's where one of the most promising, relatively new techniques is gravitational lensing, which is what I will describe to you next. So gravitational lensing is a phenomenon which again comes out of Einstein's theory of general relativity. The concept is very simple. Light, just like everything else, feels the force of gravity. Light rays are deflected by gravitational fields. So if you send a light ray along a massive object, that light ray isn't simply going to go in a straight line, but it's going to fall a little bit, just like a tennis ball would fall if you sent it past a planet, or a satellite is bent by the gravitational field of a planet. So a light ray is deflected by the gravitational field of a planet. That's really all there is to it. And you can calculate it very simply using Einstein's theory, and Einstein, I think, was the first to do this himself. And the deflection angle is a complicated formula. It comes out as the gravitational constant, the mass of the object doing the deflection, speed of light comes in, and the distance that you get close to the lens, to the object doing the deflection. That's all you need to know to figure out what the angle of deflection is from this light ray as it comes in here and goes out in a different direction. And interestingly, if you do this calculation using Newton's theory of gravity, the old theory of gravity from before the 20th century, you would get exactly the same formula, except this factor of 2 would not be there. And so there's actually, this is one of the clearest cases where Newton's theory and Einstein's theory made different predictions. And in the 1920s, when this measurement was actually made during a solar eclipse, this is actually what turned Einstein into a superstar, because his theory was confirmed and Newton's theory was shown not to fit the data. But that's a sideline. And so the idea is that light rays that we see with our eyes or with our telescopes or with our camera are actually coming from different directions than the directions in which they were emitted. And in fact, this is something that we're all used to. It happens on Earth all the time. There's many examples where, for example, here, glass lenses or glasses, wine glasses, hot air bubbles, all these things have the same effect, that they can deflect light rays and send them in different directions. And we're actually used to living with these kind of things. But in cosmology, it's something which we can use as a tool. In particular, what we can try to do is measure how strong this deflection angle is, and from that deduce how massive the object is that's doing the deflection. And that's really the key, the core of our techniques to try to measure the masses of objects in the universe using this gravitational lensing technique. And in fact, seismology is basically the same thing using sound waves instead of using light waves. Right? Light is electromagnetic waves, and but in seismology, you launch a sound wave through the Earth and you measure where it comes out and whether it's deflected. And that tells you something about the inner structure of the Earth. We basically do seismology of the cosmos in some sense. So if you imagine what a gravitational lens does, if you have a big mass here and you send light rays past it, then you see, because this formula tells you that the effect is strongest when the radius is smallest, the biggest deflections occur when you come close to the mass, the smallest deflections occur far away from the mass, and so you get this general kind of pattern. Light rays nearby the mass get deflected a lot, light rays far away hardly feel anything at all. And typical scales in which this occurs in the sky are between minutes and seconds of arc, so very, very small angles. An arc second is basically the smallest thing that you can distinguish with a small telescope. And so you can contrast this with a normal optical lens. In a normal optical lens, in order to bring everything to a focus, you need to have the opposite. You need to have the largest deflection angle not in the middle, like for a gravitational lens, but at large radius, far from the center of the lens, so that it can get deflected to the same focus as a light ray here, which needs less deflection to get to the same point. So it's a lens, but it's a different kind of lens. It's a very different kind of lens, in fact. If you wanted to make a piece of glass that acted in the same way as a gravitational lens, you would have to make it something like this. This kind of lens gives a small deflection angle far from the center of the lens and gives a larger deflection angle closer to the middle. And you see that such a lens does not make a nice focus. All the light rays go to different places. And this is what we call, in technical term for this, is a bad lens. It's a lens which has a lot of spherical aberration, and it's not something you would want to use in normal optical systems that you would build. Now, the universe is full of structure, and so we're not talking about the effect from a single lens. We're talking about the effect of many, many lenses all sitting together. So when we observe galaxies that are far away, at the other end of the universe, let's say, we are observing them through a whole web of large-scale structure before they get to us here at this end of the diagram. And so all the light rays are continuously being deflected slightly by very small amounts, but sometimes they find a mass above them, so they're deflected up, then they find a mass to the right, so they're deflected to the right. And so they make this kind of zigzag pattern as they make their way towards us. And so we don't quite see these galaxies as they are. We see them distorted by this gravitational lensing effect that I just described. And if you look at galaxies far, far away, at significant distances beyond most of the large-scale structure in the universe, then the typical amount by which they are deflected is about 3 minutes of arc, which is about 1/10 of the diameter of the full moon. So it's not a small amount. It's something that you actually see. And so, that's, in a sense, that's a handicap, because we don't see the universe as it is. We see it distorted. It's like looking through a bad piece of glass. And so, but nonetheless, it's something that we can turn to our advantage. So if you try to measure the effect of gravitational lensing, we have the problem that we're not opticians. We're not sitting in a laboratory where you can take a piece of glass and take it out and see what the effect is. We're always looking through the universe. We cannot take the universe to the side and see what the universe would look like without all this large-scale structure. We only have one experiment. We cannot take away the lens, but what we can do is see whether the deflection is uniform or changing across the sky. And the way that works is like this. If you imagine that you have an image of a distant galaxy like this, but now imagine that all the light rays that we're observing from this galaxy are deflected by the same amount. Right? Imagine that through its way through this cosmic web, all the light rays are deflected some certain distance to the right. Then what would we see? We wouldn't see this galaxy because the light rays are deflected. Instead, what we would see is that the image is moved as a result of this deflection. Right? All the light rays are coming from a slightly different direction, but they're all coming from a different direction by the same amount. And that means that we still see the same picture. We still see the same galaxy. And since we don't know where the galaxy was originally, we have no way of telling that this galaxy has been perturbed. We cannot measure this kind of a deflection. But what we can measure is this. If you imagine that the same galaxy now is seen in a part of the sky where this side is deflected a little bit and this side is deflected a lot, for example, because there's a massive object here which bends light rays that come close to it more than light rays that are far away from it, then the effect is not that the whole picture shifts, but the whole picture shifts and is stretched. Right? This side of the galaxy is moved more than this side of the galaxy. And that changes the shape of this galaxy. Right? Now this galaxy doesn't look like this anymore, but it looks more stretched. And that's something which we can try to measure. That's something we can detect. And so even though we cannot see by how much all the sources have been moved through this effect, we can see how they've been distorted by this effect, how things have had their shapes changed. And that's really the essence of how we use gravitational lensing as a technique to try to figure out how much structure there is between us and the sources that we observe. And we call this effect, the stretching effect, we call a gravitational shear. And it's really the same as looking through a piece of bad glass. If you look through an old window, you get the same effect. Right? You see that the window is not a new window, all the glass is perfectly parallel and it has very nice optical properties. But if you look at an old window, the glass will have run, there may be bubbles in it, there may be dents and scratches. And so what you see is a distorted view of what's outside. And just like in, if you see this picture, there are two possibilities. Either the glass is perfect, but you see something, what's outside is actually something very strange with lots of little structures in it. Or, with our experience, we say the opposite. No, there's a perfectly normal building out here, but what's distorted is the glass. And in cosmology, we do the same thing. We have a good idea of what the distant universe should look like, and if we see funny patterns like this, then we attribute this to the effect of the light having been distorted on its way to us. Now, there's one other peculiarity about looking through a gravitational lens which I want to describe, and that's the following. Again, if you have an observer here trying to study some distant object back here, without the lens here, we would see these light rays. They would come straight towards us, but because the lens is here, this light ray is bent and deflected and sent somewhere else. We don't get to see it. It's somebody else on some other planet maybe gets to see it, but we don't. Instead, what we see is this light ray, which in the end was not meant for us at all. It's sent in a different direction, but is deflected here by just the right amount to make it back to our eye. Right? And so what we think is that when we see this, what we say is, I have light coming from here, so the source must be somewhere up here. Right? That's another illustration of the effect of this distortion. And if you think about it, what this means is that this source, which in reality is quite close behind the object doing the lensing, in fact, it appears on the sky further away from that source. So if I give you the same picture but seen on the sky, instead of seeing this, where this source is seen projected quite close to the lens, just behind it, instead, because of the gravitational lensing, the image is, if you like, pushed away from the lens. So the stronger this gravitational lens, the bigger this deflection angle, the more the detour that the light makes, and the further away you will see the image from where it was supposed to be. And so in the first instance, this is counterintuitive because gravity is an attractive force, so you do expect that the light is attracted towards the lens. But the effect on the sky is actually that a massive object pushes the background sources away from it. Right? It looks like you're sort of squeezing to make extra room in the sky by this lensing effect. And fundamentally, the reason for that is that we're following the light rays backwards, and so we're seeing the effect in reverse. But so the fundamental effect is that whenever you look at a region of the sky where there's a massive object in the foreground, all the background sources around it will have been pushed slightly away from it. And because they're pushed to different degrees, then you're not pushing the lens equally far. You end up not only pushing them away, but also distorting them slightly. And so greatly exaggerated, this is the effect that you tend to see, that sources around a massive object are aligned in a kind of tangentially stretched pattern like this around massive objects. And so this is the pattern that we look for to try to detect the gravitational lensing effect. Wherever you see this kind of a pattern, you have to suspect that there's something in the foreground that's causing this gravitational lensing. Okay. And it's illustrated here in a different way. If you imagine that the distant universe was very kind to us and was a beautiful graph paper that you can do nice measurements with, if you take that and you put a gravitational lens in front of it, from left to right, the lens is made stronger and stronger and stronger in this calculation. Then you can see on this graph paper also this pushing away effect, this stretching effect. The stronger the lens, the more the images are pushed away from the lens. And in fact, if you take a wine glass and you put it on a tablecloth and you look through the base of the wine glass, you see exactly this. So afterwards, if you feel like it, you can try this. Maybe I will. But of course, the universe is not so kind as to give us graph paper on the distant sky. Otherwise, we would be able to make these measurements very easily. Instead, the universe simply provides lots of galaxies, lots of sources, lots of independent sources. And so these sources just look like little round blobs, and we don't know where they are supposed to be. So we don't have the reference of the graph paper. So this is exactly the same plot as I showed you before, but now replacing the graph paper by just random dots in random places. And then you see that from the positions, you can no longer tell that there's gravitational lensing, But you can still see the squeezing effect. You can still see, particularly in the stronger case, and if you train your eye to recognize this pattern, you can see it here too, that there is a tendency for the objects to be aligned in a kind of tangential pattern around the center of the lens. Right? They're no longer round like they were here, but they're stretched along this direction, along this direction, along this direction, along this direction. That's the pattern that we look for. Now, in fact, even this is too kind. The universe is even less kind than this because the sources that we see are not simple round blobs. They're galaxies of all possible shapes and sizes. And so this is a more realistic picture of what we have to work with. Right? Here we have basically a random collection of galaxy images behind the gravitational lens. And then you see it gets a lot more difficult to detect this effect. Because for each individual galaxy, you don't know, but you would like to know what the intrinsic shape was before it was distorted by the gravitational lens. And all you can do is look for a kind of coherent distortion, a tendency for galaxies to align tangentially. But you cannot do it galaxy by galaxy anymore. And so there are statistical techniques, which maybe I will not go into detail on here, for how you would take a picture like this and turn it into a detection of gravitational lensing. Basically, what you would do is you take every galaxy, you measure its ellipticity, you put it in a diagram like this, which is an ellipticity diagram, and then for every galaxy, you figure out how this ellipticity is distributed. When there's no lensing, you would find a nice round distribution of points centered nicely in the middle of this diagram. The average galaxy is round, but if you imagine that this whole piece of the sky is stretched, then in this diagram, the whole cloud is moved, and you can detect this centroid shift as a detection of gravitational lensing. That's how we do it in practice. Here's a computer simulation of the effect, which shows what happens when you put a whole bunch of foreground masses and you move blue background sources behind it. And you see again the same effect. If you follow an individual blue source, you see that it doesn't travel in a straight line, but it takes a detour around this massive region in the surface. Again, it's the same lens pushing away the source effect that I've described before. Okay, and this is a real case. So the previous one was a computer simulation. This is a real gravitational lens in the sky. All the yellow objects here are a cluster of massive galaxies, one of the most massive galaxy clusters that we know. And what you see, if you look carefully, is that many of the faint background sources are aligned in these nice little arcs tangentially around the massive object. You see some nice ones here. It's not quite dark enough to see them properly, but these, if you go to the Space Telescope website and you look for gravitational lenses, you see many beautiful cases of this, where we see these tangential arcs caused by the gravitational lens. And incidentally, the only way to explain this effect in the magnitude that we see is once again to add an awful lot of dark matter, about 10 times as much matter as we can infer from the starlight here, to make the lens strong enough to give the effect that we observe here. Okay, so I hope I've conveyed the idea that this effect is A, real, but B, difficult to measure. And the reason it's difficult to measure is that the background sky is so chaotic. It doesn't consist of grid paper. It doesn't consist of beautiful round objects. It consists of random galaxies and random different shapes. And so you really have to statistically look for alignments and see whether in a part of the sky there are as many galaxies oriented this way as this way, this way as this way, this way as this way, etc. Or whether there is, if you stretch this whole image, whether there is a tendency for the galaxies to be all aligned in this direction, or if you squeeze it, all aligned in this direction. That's the kind of measurements we have. If you want to measure this in practice, you run into other problems. The main one is the atmosphere of the Earth that we have to observe through. Even on very good sites, on the best astronomical observatories, the atmosphere is not perfectly stable. There's some blurring. That's why stars twinkle at night. And so that means that the atmosphere makes your images slightly less sharp than they would be without. And so this blurring spoils your images. It spoils your ability to measure very, very accurately the shapes of galaxies. You also have optical effects in the telescope, and you also have things that happen even in the detector itself. And so it's kind of ironic to think that I was talking about observing galaxies 8,000 million light years away, so light that has been traveling to us for 8,000 million years, and everything's fine. These pieces of these light particles are just doing nothing. They're nicely preserving their message to us, and then they come to Earth, and what happens? They go through the atmosphere, which takes about a microsecond, and they get disturbed, and then they go through a telescope, which is the last nanosecond of their 8,000 million year journey, and they get disturbed even more, and then the last picosecond they go through a detector and they get destroyed and disturbed even more. And so it's kind of sad to think of these, the signal, which has been traveling to us for 8,000 million years, getting destroyed in the last microsecond and smaller. But it's the way it is. It's the best we can do. And so now we're able to not only detect this gravitational lensing effect and measure it, but we're able to do tomography with it. We're able to use this to trace the three-dimensional structure of the universe, of the mass distribution. And that's, as I explained before, is what we need to try to put constraints on the dark matter and the dark energy evolution. So, and the way this works is it's not too different from a CAT scan or any kind of other tomographic device. If you observe, this is us observing, if you observe galaxies at different distances down a line of sight, then the most distant ones, their light is deflected by all the matter, all the lenses along the line of sight, but the nearby ones only feel the lenses that are between you and them. Right? The light that goes from here to here has no knowledge about what happens behind it. And so by comparing the lensing effect on this source, on this source, on this source, on this source, you can try to sort of peel off the effect of this lens and then the effect of this lens, the effect of this lens, and so on. So you can reconstruct the full three-dimensional picture by comparing the lensing effect to ever more distant sources. And so that's really how we get our three-dimensional picture. Again, it's not easy. The measurements are very complicated. It's easy to make mistakes, but this is what we're trying to do and getting better and better at. So motivated by the questions of trying to understand the dark matter and the dark energy, and by what we can now do with this gravitational lensing effect, we have started a new experiment. We've built a new dedicated instrument, and in the last third of my talk, I would like to tell you a little bit about this. And it's motivated, as I said, by measuring this lensing effect better than we have been able to do before for a huge number of galaxies, so that we can really get the statistical measurement to make an accurate determination of the distribution of dark matter and its evolution with distance. So we need to make these very accurate measurements, which means we need to make very good, sharp, high-fidelity images. We need to average the shapes of many galaxies to get good statistical accuracy. So that means observe a large part of the sky. You need to have an instrument that can take large pictures. And to do the three-dimensional aspect, you need to measure the redshift of the galaxies very accurately. You need to be able to get the spectral information. And that means you need very accurate colors of the galaxies so that you can be able to do this tomography. And so that's the project that I'm going to describe is called the KIDS project. It stands for Kilo Degree Survey. It's more than 1,000 square degrees of sky that we're going to observe to try to really measure this effect in great detail and try to make the next step. It uses two new telescopes that have been built at ESO, the European Southern Observatory, which is a European organization that runs, I think at the moment, the most advanced observatory in the world. It's a multinational intergovernmental organization. Spain is a member, Holland is a member, it's 14 countries in total. And it really provides fantastic facilities for us all to use. For one of these two new telescopes, we designed specifically a new camera that combines both being able to take large images to catch many galaxies at once and measure very accurate image quality. And this past year has been very exciting because we got to the point where we entered into operations. We put the camera on the telescope for the first time early this year, and now we're at the point where we can use it routinely. And all these are large projects, so this involves collaborations with many of our colleagues and friends in different countries across Europe. So this is the heart of this instrument. The instrument is called Omega Cam. Omega is the symbol that we use for angle on the sky, and so it's a capital Omega because we can do a large angle on the sky. And it's basically, at its heart, it's a digital camera consisting of a mosaic of detectors, and in total, it's something like 300 million pixels. So even the best digital cameras that people work with now are maybe a few tens of million pixels. This whole thing, which is about this large, is about 300 billion very, very sensitive pixels of digital camera. Now that's the heart of it, but to be able to make it work, you need an awful lot of instrumentation around it. These instruments are at their most sensitive when they work at about minus 140 degrees Celsius, so you need to cool them. So there's a huge cooling installation that sits around it. This detector system sits here at the top of this large cooling device. We have to pass the light through colored glass filters to be able to make these color measurements that I described. And again, these filters have to be such high optical quality that they don't destroy the image quality that we are after. Because it's so large, you need to have a shutter. Like in a camera, you have a shutter to get a picture here. The shutter is very large to be able to close the exposure. As you can see, the shutter was made in Germany, but it's a large thing. So they didn't have to think very hard before they found the right reference to show the size. They're very proud of this. And then when we had all these things together, we put them all into a big, heavy, solid, strong, light-tight container so that we can make the measurements. And this is the team that put the instrument together before we shipped it to Chile. Then we take it to this amazing place. This is Paranal Observatory, which is run by ESO, by the European Southern Observatory. It's in the Atacama Desert in Chile, just south of Antofagasta, here. And so this year I've spent a total of several months trying to get this instrument to work properly. So it's really the most advanced place in the world. It's almost literally out of this world, because it's a desert with absolutely nothing, and then suddenly one of these mountaintops is covered with literally more than €1 billion of toys for astronomers. It's fantastic. So these big four things are large, huge telescopes with a primary mirror of 8 meters diameter. So I can't do this with my arms. It's about the size of this stage. And then the smaller telescopes are done for interferometry. And the telescopes I'm going to be talking about, which are the two new ones, are the two survey telescopes, which is this one here and this one here. And those are specifically designed for making large maps of the sky. Here's another picture just to show you that it's nice. So they really have to blast the top of these mountains to make enough space to build all these telescopes on the top. The observatory is very close to the coast, and most of the time the wind comes from the sea towards the observatory, and that means that you have a beautiful parallel low turbulence flow, which means that when the air that flows over the observatory doesn't have turbulence, and so doesn't disturb the beautiful image quality that you get. And of course, the other thing you can see is that everything is very brown here. There's no vegetation there at all, which is a very good sign, because that means it doesn't rain. And if it doesn't rain, there's no clouds. And if there's no clouds, you can see the stars. So if you go to an observatory that's green, that's always a bad sign. So this one is not green, I can tell you. So I told you about the camera, OmegaCam, the instrument that we built for one of these two new telescopes. The telescope that this camera went on is called the VLT Survey Telescope. VLT stands for the Very Large Telescope, which is those big 4 telescopes. This is part of the same complex, but it's a separate telescope, which we call the VST. And it's built by the Naples Observatory in Italy for ESO to run and use. And so projects like this start with a design phase, with a paper phase, where you try to design the optics in such a way that at least on paper you can achieve the image quality that you want. So the light comes in, this is the telescope on its side, this is the primary mirror, which catches the light that comes from the universe out here. So the light starts here on the left, flows in, bounces off this mirror, bounces back off the secondary mirror, and then down here through some lenses into the instrument, and our OmegaCam would be here at the back of the telescope. So the most important part is the primary mirror that really sets the optical performance. And here is an old picture of the primary mirror, beautifully polished. You see lots of instruments here which are used to subtly change the shape of the mirror to really keep it in as perfect a shape as you possibly can. And this is a picture from 2001, and unfortunately this is an old picture, and the reason for that is that when this mirror was finished and shipped to Chile and unpacked, this is what it looked like. So something had happened in transport, unfortunately. This mirror, which cost more than €1 million, was turned into very expensive paperweights for people to put on their desk. Somebody dropped the box somewhere in a ship, somewhere in the transport between Europe and Chile, unfortunately. So that was 2002, which, as you can imagine, was a major setback for a number of us who were involved in this project. Now, I'm not in Holland, there is a saying, and it may be the same in Spain, that if you break a mirror, it's 7 years of bad luck. So that was 2002. And so in 2009, indeed, the telescope was there and was being erected. And so at the beginning of 2011, in this enclosure on the platform on Paranal Observatory, there was indeed a new telescope with a new, beautifully shaped primary mirror, which this time arrived in one piece. And so earlier this year, we managed to attach the instrument to the telescope. You see there's a zillion cables there because there's so many complex functions that you have to be able to control inside this instrument from outside. And also all the data from these detectors has to be taken out of this very cold environment into the readout electronics and into the computers that are used to produce the data. So, but anyway, at the end of March of this year, this was the instrument mounted and ready for use on the back of the telescope there at the bottom. So finally, the moment we'd been waiting for. And so in the past 6 months, we've spent a lot of time trying to get the instrument to work, to really tune the image quality to make the kind of images that we want to take. Also learning how to use it efficiently and operationally and so on. But in the meantime, we had the chance to just take some beautiful pictures of the sky. And after all, we're all astronomers, and that's actually what we want to do, is just take beautiful pictures. And so here's one example. This is an area of the sky in the constellation of Leo, of the Lion, where there are 3 big galaxies in a group. They're all at the same distance, so they all feel each other's effect, and they're influencing each other. You can see that this galaxy is a bit distorted. That's because of the gravitational field of the other ones. And just to give you an idea, it used to be that to take pictures of this, you would have to take a picture of this galaxy, and then a picture of this galaxy, and then a picture of this galaxy, simply because the field of view of these cameras was not big enough to take this whole picture in one go. But with our instrument, we're able to cover an area which is twice the diameter of the full moon. This is the size of the full moon, just in one shot. So we're able to really do large parts of the sky in one go. And so there's we've taken many other pretty pictures. And again, it's a little bit too bright in here to do full justice to them. This is a region in our own galaxy where there's a lot of stars being formed, and the gas around them is being lit up by the newly formed stars. This is the moon, as you can guess. This is a zoom in on another area where new stars are being born here at these tips, called the Eagle Nebula. And there is actually a very famous space telescope picture of the same area called the Pillars of Creation that many of you may have seen. And I'm not going to claim that our picture is better than the space telescope picture, but it's pretty close. I'm pretty proud of this one. You can also just take random parts of the sky and simply study the distribution of galaxies. And here, for example, we have an area where there's a lot what's called a supercluster. So many clusters of galaxies are coming together here for the first time, and under the action of gravity, they're slowly falling together. And sometimes there's very large objects on the sky, like this beautiful nebula of about 10 million stars called Omega Centauri, one of the jewels in the southern sky. So every once in a while we do something for the aesthetics also, because it makes us happy. So here again is the Leiden Observatory, and so what's going to happen next is that this KIDS project that's going to do a large 9-color map is going to start using these 2 telescopes, VISTA, which is a telescope that works in the near infrared, and wavelength slightly longer than the reddest light that we can see with our eyes, and the VST, which is this telescope here with our own Omega camera. And on these 2 telescopes together, almost 700 nights of observing time have been allocated, which makes it one of the largest observing projects that are around at the moment. And we started taking data about a month ago, so finally we're able to get this long-awaited project, which certainly when the mirror broke, we thought might never happen, and it's very gratifying to see that we're there now. Oops. So you weren't supposed to see that. So what are we going to do? We're going to observe these areas. This is a picture of the entire sky projected onto the screen here, and in green is the area of the KIDS survey. So there's a northern part and a southern part, designed so that at any time of year there's always some part which is above the horizon that we can observe. And these 2 things together are something like 7% of the extragalactic sky, of the sky outside the part that's blocked by our own galaxy. And to get an idea of how much that is, that the fraction of the sky that we're going to observe with the KIDS project is about the equivalent to the fraction of the globe of the Earth that's covered by the continent of South America. And if you think about how big the pixels are, what resolution we're going to achieve, what we're going to do is actually equivalent to making a map of South America at a resolution of 5 meters. So it's a lot of work. It's going to be a lot of data, a lot of images to process. And so, as you already saw, it's a lot of data, and we have to be very careful that we don't get completely overwhelmed by all these data that we're going to start receiving very soon. And the reason why it's a lot of data is that we're doing such a large area of the sky, but at the same time we want to have very fine resolution, so we need many pixels on every part of the sky. And so in practice what we're going to do is just go one image at a time, side by side, and slowly build up our map, image by image. And each of the parts of the sky that we will observe through 9 different filters to get the 9-color image, which is what we need to get the high accuracy redshift information. And you can do the sums. Every galaxy is every image is about 1 gigabyte of data, 9 colors, and 1,500 patches to get our full 1,500 square degree map. So this is in total going to be about 30 or 40 terabytes of data that we will have of images that we will have to analyze for our project. So the disadvantage of having to wait is that we had to wait. The advantage is that we had time to get ready, and that computers had time to get faster and able to process large amounts of data. So we spent a lot of time in the meantime preparing our computer archive and our system to be able to process these data more or less routinely. And now that we've started, it turns out that many of these investments have actually turned out to be worthwhile. Okay. So what are we going to do? We're going to make this large 9-color map. We can look back about 8,000 million years ago to when the universe was about half the size that it is at the moment. And that's actually the epoch during which most of the effects of the dark energy were felt. So that's the interesting epoch to try to study with our gravitational lensing technique. And what we're going to do is map out, using the gravitational lensing effect, the distribution of matter as a function of look-back time, and therefore get this 3-dimensional picture, this history of the growth of structure over this time, over these last 8,000 million years ago. So that'll tell us about the expansion history of the universe and about how the growth of structure, and those two things together are the ingredients that we need to try to understand how and how fast the dark energy took hold and how the dark matter is distributed and was distributed in the past. And this is really the kind of information that we need to try to provide hints to where, whether our simple understanding, our simple ideas of what the dark energy might be or the dark matter might be, to try to provide hints to do this more. But of course, to most astronomers, this would actually be a very boring goal, because all you're doing is taking lots of galaxies, putting them in the computer, and getting out a few numbers after weeks and weeks of processing. Fortunately, it involves taking pictures of the sky, and this means in the meantime you could do an awful lot of wonderful astronomy. You just come across all kinds of beautiful sources, and so that's actually, for me personally, the aesthetic part of this whole endeavor is actually what keeps me going. It's not the final number in 5 years' time. That'll be very interesting and I hope very worthwhile. But in the meantime, what keeps you going is the fact that you're always working with beautiful images of the sky. In many cases, parts of the sky that nobody has looked at before in this kind of detail. Okay, now we're not alone, but at the moment we're ahead. There are other experiments on different observatories trying to do the same sort of thing, make the same kind of maps. People have made slightly different choices about how big the map should be, how sensitive it should be. I think we're in good shape in this competition, but there are very ambitious ideas to build new telescopes in Hawaii, for example, the Pan-STARRS project here. There's an experiment called the Dark Energy Survey, which is going to do something quite similar to KIDS from a different mountain in Chile. Where there's an American observatory, which is not as good as the European Observatory. I have to be careful, I'm being filmed, but I think it's true. And in the end, there will be, the people are dreaming of new monsters, such as this telescope. This is a human, this is a person. So this is a giant 6-meter survey telescope, which can take very large images with great sensitivity very fast, which might be operational towards the end of this decade. Called LSST, is called the Large Synoptic Survey Telescope. So many ambitious projects to try to do similar science and other things as well. And the reason that there are many people doing this is that it's a very important problem in cosmology at the moment. Ultimately, to be able to make the best measurements with the best image quality and the most stable conditions, you need to get away from the atmosphere, which, as I explained, blurs our images slightly. So in the end, you want to go to space. You want to launch a satellite above the atmosphere. And the European Space Agency, ESA, has actually just this past October selected the next 2 science missions, which will be launched towards the end of this decade. And one of them is called Euclid, and is a mission to do precisely this. It's precisely a dark energy mission, intended to use particularly gravitational lensing to try to do the kind of experiment that I described, but with higher fidelity and with greater sensitivity. So the fact that this mission was selected after 2 years of hard work convincing ESA that this was really the top science case that they should be focusing on was extremely gratifying for this whole field, and it actually stimulated all the ground-based surveys, including KIDS, it really means that we're going somewhere, that we have a time horizon that we have to deliver, and also it means that we will learn an awful lot about how to properly process the data that comes from Euclid using all the things that we will learn now, both about the universe but also about techniques until the satellite is launched. So these are perfect pilot experiments for this, if you like, this ultimate science mission, addressing the same science questions. Okay, so I'm at the end of my story. Let me remind you briefly what we showed, what I discussed. So the first third of my talk, I tried to sketch the background of how cosmology, of the picture of cosmologists of the universe at the moment, how we started from very uniform initial conditions through gravitational instability to the growth of structure that looks very similar to the distribution of galaxies that we observe today. I showed you how the Hubble diagram for supernovae gave this very surprising result, for which the Nobel Prize was awarded last month, that the acceleration of the universe is not being slowed down as we expect from the effect of gravity, but is somehow being accelerated by some new effect, which we've called dark energy, and how if you put this all together, you end up with this very unsatisfactory pizza that nobody ordered, right? The contents of the universe in a pie diagram here. Then I explained how gravitational lensing works, how masses act to focus light rays from behind them to give you optical effects which we can use to our advantage to measure the distribution of masses in the universe, a little bit like looking through imperfect glass, trying to understand how things work. And then in the last third, I described the instrument that we built for the VST survey telescope, the sky survey that we're going to do, the KIDS project, the awful lot of data that we're looking forward to getting, and how ultimately this is going to end up with a space mission that will do everything we can. So to end with, we're getting to the point where we're observing everything we can about the sky. We're considering now maps of the entire sky. Once we've done the entire sky, we've done the entire sky. All you can do is look again with more resolution or more sensitivity, but there's only one sky, and we're about to finish it, if you like. So in some very real sense, the sky is the limit. That's as much as we can learn about the universe. We can only look back 13 billion years ago. We can only see a finite section of the universe. It's very large, but it's finite. But nonetheless, we're not there yet, and so it's actually a very exciting time to be a cosmologist. So to close, I should say that the work I'm describing, of course, is not just my own. This involves large science teams with lots of students and postdocs and colleagues from all around the world who are involved in thinking on how to do these projects and also in actually doing a lot of the hard work. And so astronomy in that sense is a nice small science community which is spread over the whole world, and so it's actually also a very nice illustration of how this global village on this really tiny planet of ours can try to do great things. And with that, I would like to thank you for your attention and for coming. Thank you.